Good evening, everyone, and welcome to the 2025 DSACT Research Conference. We are thrilled to have you here today as we explore groundbreaking developments and innovative research focused on improving the lives of individuals with Down syndrome. Your presence here underscores our shared commitment to advancing knowledge, collaboration, and meaningful support in our community. It is now my privilege to introduce to you our keynote speaker, Dr. Jon Pierce, whose remarkable journey as a scientist, father, and advocate has profoundly shaped his life's work. Dr. Pierce earned his doctorate in neurogenetics from the University of Oregon in 2000, going on to study as postdoctoral fellow at the University of California, San Francisco. During this time, he welcomed his first son born with Down syndrome. Since establishing his lab at the University of Texas in Austin in 2008, Dr. Pierce has led a dynamic team of researchers working to unlock causes, potential cures of genetic disorders through cutting-edge research. His influence extends well beyond the lab. Locally, he founded Lifelong Learning with Friends, a continuing education program empowering adults with Down syndrome and other disabilities. On an international scale, Dr. Pierce serves as General Secretary of the Trisomy 21 Research Society, the leading global organization uniting scientists and medical professionals dedicated to Down syndrome research. We are honored to have Dr. Pierce with us today, and we look forward to hearing his insights and inspiration. Please join me in warmly welcoming Dr. Jon Pierce.
Thank you. Do you want, I should go ahead and use the speaker, I guess? Sure, why not? So yeah, thank you for having me, encouraging me to host this. I'm here actually because of you. I'm doing Down syndrome research because of DSACT. When I moved to Texas with our family in 2008 or so, just within a month or so, you guys hosted a public research event like this, and you invited Bill Mobley, who's now chair of neurology at UCSD, and I showed up at that event not knowing any of the DSACT members, or anyone in Austin for that matter. I walked up to Bill Mobley and I said, "Hi, I'm a new researcher on campus. I just got hired to study alcohol. Maybe after I get tenure, I'll study Down syndrome." And I don't know, some of you were probably at that event. At the end of the event, Bill Mobley, talking to a much larger crowd, he's a more famous researcher than I, he said, "You guys are so lucky to have a famous Down syndrome, or a great Down syndrome researcher here at UT." And I knew that they had no Down syndrome researcher. I was very confused what he's talking about. He said, "Jon Pierce, stand up." He didn't even know who it was. And I was standing up, I was forced to stand up, and all these people are applauding for me, and I had no mission or prerogative. My bosses did not want me to study Down syndrome. They hired me to study alcohol, and that was very awkward. And then I moved on, weeks later, like Bill went, he left, and I had to show up at DSACT events, and you guys would say, "What did you discover this week on Down syndrome?" It's very awkward, week after week, asking these questions and not having an answer. So that pushed me to study Down syndrome faster than I would have otherwise. As he said, I'm here today to kind of share some exciting research developments over the past 5 years or so around the world. And I have a terrific vantage here as General Secretary of the Trisomy 21 Research Society. We just had a meeting this morning, and it's just remarkable how they've connected about 500 or so researchers around the world who are dedicated to this cause, to helping our kids with Down syndrome. And I was looking at my notes. We did a version of this, I don't know, about 5, pre-COVID. There's so much more to talk about there. I can't even have room for all the slides, all the cool things that are going on. So that's an exciting place to be. Through these years, I've met luminaries like Bill Mobley, Roger Reeves, Myra Deason, Alberta Costa. Maybe you guys have met some of these wonderful people. And there's just so much more. So what I thought it'd be fun tonight for us to do is I'll give you a sampling of some discoveries that have been made over the past 5 years or so by different researchers, not me. And then I'll turn the mic over to my grad student, Swetha Iyer here, who can share what she's been doing and other people in my lab have been doing on Down syndrome research. And I'm really excited about this cool discovery that we had. It's much bigger than I ever anticipated it could be. It just shows why people should be funding Down syndrome research, because it's going to end up probably benefiting thousands of medical conditions, and totally unexpected. And then last, we'll hand the mic over to our group here with Chloe Jones and their group, and they're doing human clinical trials with people with Down syndrome, and they can share what they're doing. And this will be, I think, a good mix of topics. So why am I here? I'm here because of you, but firstly because of him. This is my son, Ocean. So he's my inspiration to start research, and when research isn't going fast, push for doing something, so we have educational outreach programs here. He's right now across campus in one of these classes. So if you haven't heard of Lifetime Learning with Friends, please check it out. We have serve over 400 people with disabilities each year, with about that many number of UT undergrad students with dozens and dozens of classes. So yeah, check it out. And I'm really happy that we have a lot of people here from Best Buddies, by the way. I have the privilege of working with students from Best Buddies. They're a fantastic student org here. It's just incredible the social activities they put together for our kids. So how do we know, what is Down syndrome? Perhaps you know this already here at Ocean. After he was born, we didn't realize he had Down syndrome until a month later. He went back to the NICU, and a nurse kind of guessed that he might have Down syndrome. And so when that happens, they do a karyotype to count the number of chromosomes. So he has a very simple case of Down syndrome with trisomy 21, a full extra copy of the 21st chromosome. So this is, so Down syndrome is caused by problems, right there, somewhere on that piece of DNA that's all coiled up. That's where the problem is. It can give rise to problems, but also some superpowers too that we'll talk about today. It's been known since the 50s that it's the extra chromosome that causes this. But now we're in the position with a list of genes on the 21st chromosome to try to figure out what genes are causing these problems. In parallel, another strategy is to try to figure out how is physiology or messed up, or how can we push it back towards typical. And one way to think about with from the gene perspective is thinking about recipes and which ingredient can we afford to have as extra copies or not. And which ones are these? And Swetha's going to talk about that a bit later. One of the more exciting parts of Down syndrome research across the United States right now is this trial-ready cohort that Floyd will talk a bit more. You're part of this. What's exciting in this is not only can people with Down syndrome participate in this system of clinical trials, but once you're in the system, they can alert you to new clinical trials that are there it would help your specific individual with Down syndrome. And that's pretty cool. It's not a one-off and write-off. You'll be there and they'll be looking out for you. And they'll talk more about that. So yeah, Dr. Rafi's primarily focused with this cohort on looking for what factors predict age of onset of Alzheimer's or severity. And this is unfortunately something that's very high risk in individuals with Down syndrome. I'm sure you guys are going to talk about that later. Some other things that are new are over the past 5 years or so, researchers have a much better understanding of Down syndrome regression disorder. I think this has affected some people locally. When I first heard about this, I didn't know much about it. It thankfully is relatively rare, but not rare enough. This is a situation that's believed now to be caused by a dysregulation of immune signaling in individuals with Down syndrome. One of the known causes of dysregulation is there are genes for interferon receptors. This is a type of immune signaling So with this extra load of genes on that for these receptors, that can tip how the immune system responds. And one scary form of response is regression disorder. This is where someone with Down syndrome can suddenly, fairly rapidly lose abilities that they had before, like lose the ability to speak, lose the ability to move. They can become catatonic at times. They can lose their ability to write, or especially learned activities that they were able to do before. And this has been really kind of mysterious because we haven't really known what causes this. And there can be different causes. Down syndrome is not the only condition that's associated with regression disorder. There are other types of neurological conditions that regression can happen. And I'm highlighting research that's been pushed by Jon Pierce. He's at UCLA. He's made a lot of progress in understanding this and, importantly, treating this. So, for instance, within Down syndrome in particular, there could be types of regression that are seen at young ages that are associated with epilepsy. So, if young kids with Down syndrome have epilepsy and it gets bad, they can have changes in the brain that can lead to some of these regression symptoms. If autism can also co-occur with Down syndrome. It's, from what I understand, it's about 15% of adults, of people with Down syndrome also have a form of autism, and that can be, that can show up a bit later than it might otherwise, and that could explain some forms of regression. Now, maybe in the teens or early 20s, this is what we're focused on today. This is the Down syndrome regression disorder that can have some pretty scary symptoms here. But Jon Pierce made some progress. Much later, with Alzheimer's disease, people with or without Down syndrome that get Alzheimer's pathology, they can also develop regression, lose their abilities too. And throughout life, there could be other reasons. But today, I just want to focus just a little bit on this teen to 20s form of regression. Again, some of the symptoms to watch out for are insomnia. Sleep gets really upside down. Catatonia that's a real wake-up call if they can't move or become locked in odd posture. Obsessive compulsions. This is the point where it continues on for quite some time, and it's a new obsession. Hallucinations are also a wake-up call. That doesn't normally happen in Down syndrome. So if they talk and they tell you that they hear people talking to them or see things that are not there, that's definitely a red flag, and you should talk to your doctor. This is an important time for me to mention I'm not a medical doctor. I'm a basic researcher, but care about things, and I could try to connect you if you're local with doctors here in town that could try to help your loved one with Down syndrome if they have something like this. So one interesting aspect of this is it usually correlates with skin issues, which I think a lot of people with Down syndrome have skin issues, and some of them can include skin issues such as losing hair or having rashes. Some rashes aren't even apparent just by looking, but you might need to use your doctor might need to use a UV light or something to see different colored patches of skin. And this all relates to how the immune system is kind of acting weird and attacking different parts of your body, including your skin and presumably parts of their brain, and changing their behavior. There's like a lot more that can be said about this. I could connect you with Jon Pierce or some of the talks that he's given, but I wanted to just end on this piece that he and his work with a large number of people that have Down syndrome regression disorder, and usually the first line of medicine is to try seizure medication, because that can be a cause of regression, and it can have some benefit in some people, but more and more it looks like treating this more as an immune disorder works much better, especially if it's caught within 2 years of its first manifestation. And those people do show recovery. Now here's a strain that he has for like a score of returning back to baseline for some patients. You can see that treating with infusions of IgG antibodies to try to renormalize immune function can have a really beneficial effect. And I think we have some people here who could speak to this if you wanted to hear more direct stories. So I just want to celebrate that this is, it was not guaranteed that there was going to be any treatment for this sort of really terrible condition, but it's great that there is now, and we're studying more. This leads to another idea. This and the other skin conditions that a lot of our loved ones with Down syndrome have can be related to autoimmune type reactions or dysregulated immune functioning. So we probably all know someone with Down syndrome that has hair loss, either total or partial. It's extremely common. My son Ocean, he has kind of weird skin sensitivities now and then that just come and go. That goes along with Down syndrome. And even if they don't necessarily have Down syndrome regression disorder, they could have, it's really intriguing to think about what other symptoms could be treated if we thought of treating Down syndrome as an immune disorder. So this is, I'm just highlighting Dr. Joaquin Espinosa. He's director of the Cernic Institute for Down syndrome in Colorado. He's done a number of exciting studies recently. Here's just one over here. They took lots of people with Down syndrome. They took their blood and a few other tissues and compared to their siblings, and they tested how their genes are high or low across the whole genome. And when they did this, they were able to use that information to classify them into different groups. When they did this, they found that there are kind of 3 general groups at this stage. And they all are characterized by different types of dysregulated, unique ways of dysregulated immune functioning. One group of these looks like they might be good candidates for a drug that people are already using for arthritis. So it's already working for that, and this is called a JAK inhibitor. And there are clinical studies going now with this. You could check that out if you want. And it's pretty exciting. It remains to be seen if this sort of thing could also be combined with treating Down syndrome regression disorder. But this is definitely something to think about if it could help out with some of the autoimmune things. Other autoimmune related issues in Down syndrome include hypothyroid disorders or diabetes, type 1 diabetes. This is where the immune system's attacking your pancreas or your thyroid. Or celiac disease is another one. My son has that one. These are all autoimmune disorders that are a bit higher risk in Down syndrome. Another researcher I'd like to highlight is Andre Stredham, a former president of T21RS. He's taken tons of data from the UK Biobank to try to look at what sort of medical issues people with Down syndrome have versus the general population or people with other intellectual disabilities to see if there's any good or bad news and what's happening at different ages. One of the biggest issues, and I think other research kind of hinted at this, but he's shown that sleep apnea is pretty common in youth and younger people with Down syndrome, but can go down to normal levels as they age. Other aging conditions or cataracts are much more common in Down syndrome than the general population, and not much more for osteoporosis. Down syndrome, I wish when my son was born they told us that he had some superpowers and not just medical problems. People with Down syndrome, it's been known for a while, and Dr. Stredham's data supports this, is that hypertension, it's really rare for adults with Down syndrome to get heart attacks. it just hardly happens. And that has nothing to do with them. Even if they're obese, it doesn't happen that much. And you can see here, cholesterol problems that are severe are also at lower risk. And so are solid tumor cancers. That's much lower risk than in the typical population. But hyperthyroidism, which I just mentioned before, continues to be a problem throughout life, and that probably relates to this autoimmune disorder. And same with endocrine disorders are a bit higher. Other Alzheimer's usually takes off, around beginning near age 40 and increases after that. And that's associated also with seizures that might co-occur with that. So these are some of his findings. When he looked at all these different things, other good news was the anxiety disorders were also, on average, lower than the general population or mood disorders. But we still need to worry about some of these other issues. The things that were kind of, the things that I think people might not know to look out for is sleep apnea is much more severe than you might think. I think with my son, they had his adenoids out. These are sort of that, along with other things, are common things that people could check out for. So, pay attention to these sorts of medical conditions that are much higher risk in people with Down syndrome. Scientists also study people with partial trisomy. I don't know if you've ever heard of this. My son has an extra chromosome. Some people have an extra part of the 21st chromosome. It's pretty rare. Not everyone has this. Sometimes it might get stuck on another chromosome and they might inherit that. I think I know one case in Austin where they have siblings with Down syndrome. They both probably, because it's stuck on one of their parents' chromosomes, and they have it because of this. For scientists, this can be helpful in an interesting case because they don't have the entire 21st chromosome. You can try to figure out, okay, what part do they have? What genes are there? Maybe those include some of the causal genes that cause certain medical problems. And this is a case that's unusual, where this person has a relatively small segment of the 21st chromosome. And there's a gene there that I highlighted called DYRK1A. This is a gene that's getting a lot of attention recently as maybe a culprit in causing problems of development and neuronal function. I'll come back to that later. Here's another fascinating discovery by Jean Lawrence at UMass. She is an expert in how DNA chromosomes can condense and form what are called Barr bodies. So all the women in this room, you guys have 2 X chromosomes. I only have 1. You only need 1 per cell. So what happens for the women in this room, each one of your cells, one of them decides to get turned off and turn. You can see it here as a Barr body. And a famous example of this that you could see with your eyes are calico cats. The color spot pattern is due to these, either their mom or dad's X chromosome turning on or off, creating a pattern like that. Jean Lawrence, she figured out how the key gene on X chromosomes that activate this Barr body to turn off the chromosome. It's a gene called exist, and she transplanted that gene onto a 21st chromosome, and she could get a 21st chromosome, an extra, to turn into a Barr body, essentially turning it off. This renormalizes it, so now the cells have 2 21st chromosomes instead of 3. This is a fascinating, intriguing way to potentially treat Down syndrome. This is far from clinical trials yet, but even if this is something that is blows everyone's mind, that I don't think you would even imagine could happen. You could turn off a chromosome like that. So maybe someday that would become a practice. Another thing, here's an example of how people can study cells by taking human cells and coaxing them to become neurons and counting their synapses, or studying them, how they grow up into these organoids. These are true human cells, so sometimes other animal models don't work, but these are human cells that people like Anita work on and are making progress in studying how they're different from typical cells. Scientists also use a lot of different animal models. This is just a cute one of a chimpanzee that has the equivalent of Down syndrome. Other animals, like the rodents, they have some of the genes in the 21st chromosome that are represented not on one chromosome, but are scattered about a couple different chromosomes. So scientists have tried to study aspects of Down syndrome with rodent models. Here's one example. In Down syndrome, the back of our brain, our motor, the cerebellum, this is the part of the brain that's important for muscle memory and learning how to ride a bike or learning complicated motor tasks like handwriting or dancing. This is usually smaller in Down syndrome compared to people through typical development. Intriguingly, in rodent models of Down syndrome, here's one that Roger Reeves made that carries an extra human 21st chromosome in all of its cells. And they make the mice glow green so you can figure out which one has the Down syndrome model. When you check out its cerebellum, it's also smaller than the typical mouse. So people are using this as a model to study growth of the brain and ways to rectify that and counter that. These two researchers, Dr. Fisher and Hewlett, they recently figured out, compared the genes, their levels in mice with or without Down syndrome models and fetuses with or without Down syndrome, just for the heart. I don't know if you guys might know this, but Down syndrome is the leading congenital cause of heart defects. About half of babies with Down syndrome have an obvious heart defect. This is true with the mouse models too. And excitingly, just this past year, these researchers found that if they were to knock down the levels of that gene, DYRK1A, which I showed you in that partial trisomy, they were able to rectify some of the heart defects. They were also able to knock part of that down with treating it with a drug that could reduce that gene's action. So this is pretty exciting to see how much drugs that treat this target called DYRK1A might help people with Down syndrome. This is just to show you that Roger also made a rat, a Down syndrome rat model, and you can see that its cerebellum is also smaller than the typical rat model. And there's even zebrafish researchers there. This doesn't look much like a human brain, but they have their own version of a cerebellum. They can learn motor tasks too, and wouldn't you know it, its version of a cerebellum is smaller, and they could target that same DYRK1A gene and try to have some benefits on getting it to be larger again. And here's a friend of mine, Bing Ye. He's a fantastic researcher at University of Michigan. He uses the fruit fly. This is a research model that's been used for over 100 years and to find genes involved with different processes. And he could light up the nervous system here to glow green and notice that the synaptic wiring gets messed up during development if they have an extra version of another gene called DSACT. And he, through some real creative work, figured out that the common medicine Gleevec, this is a medicine that's used in cancer, could actually rectify how it's wired. And then lastly here, Sophie Sanchez, she's a local and legend here in Austin, and she worked in my lab, and she was able to work with tiny nematodes, and Swetha will explain some of her work and use that to figure out that's dozens and dozens of genes that might be important in Down syndrome. And Swetha will share that it's an exciting discovery. Right now, we're at this really interesting state where you can detect if, when a woman is pregnant, starting at this 10th week of pregnancy, if the fetus is happens to have Down syndrome or not. This is really changing how scientists think about Down syndrome. So much so that this next researcher, Dr. Diana Bianchi, she's the director at NIH for Child Health and Human Development. She is pushing forward the idea that potentially people could think about treating fetuses that happen to have Down syndrome. This is a kind of an eye-raising topic because what are the ethics of treating a fetus or baby? But their approach is to use chemicals or treatments that would be safe, they know are definitely safe on mothers and babies already, and just see how they can increase the likelihood that they come out as healthy as possible. So this is, she's one of the few people who's thinking this way. So I just wanted to, I think I gave you a survey. There's so much more to talk about, but I just wanted to let you know that people are studying this around the world. We actually have drugs and targets and ideas, and some of these are working. Some of these there are many clinical trials now. This is not something I could have said like a decade ago. So the research field's changed enormously. So yeah, thank you. I want to hand the mic over to Swetha.
It should be good no matter how. I think so. As opposed to. Oh, I don't.
So I introduced
Maybe it's a
Swetha Iyer. This is Swetha Iyer. She's a PhD candidate in the Interdisciplinary Sciences program here at UT Austin. She got her bachelor's in Mumbai, India, and she continued on to do some her master's at Northeastern in Boston, and she did some biotech work there for a while during the COVID era, the short COVID era before joining us here at UT. I'm excited to have her on board. She's taking the baton from Sophie Sanchez to continue this project. So she's a newcomer to the project, but she's already doing a good job, and I'm excited to have her on board.
Hello everyone, thank you Dr. Pierce for the introduction. As he mentioned, my name is Swetha Iyer, and I am a graduate student studying in Dr. Jon Pierce lab at UT. And today I am excited to share some of the cool discoveries we are making in Down syndrome research. And the hypothesis that we are working with is very simple yet a very powerful concept, which we encounter every day in our kitchen when we are cooking or baking. Since baking is often compared to science, today we will be learning some science through the process of baking a banana bread. So, what do we do first when we want to bake a banana bread? We first look up for the recipes, we look for the ingredients that we'll be needing, and then we'll also need to know how much of these ingredients do we need to make the banana bread. So, for those of you who have already baked a bunch of things, you might know that you can get away with adding some extra amount of some of the ingredients and not mess up with your recipe. But there are some ingredients that if you add excess, it will ruin your recipe. So knowing these ingredients and knowing what amounts you need to add is very important before you start making, let's say, a banana bread. But if you are going to start making a new recipe that you are unfamiliar with, let's say if you are going to make an exotic Indian recipe, Indian biryani, which requires 15 different kinds of spices. Some of those spices you might not have heard before, so you wouldn't know how much of these ingredients you need to add and still not mess up your recipe. So knowing the ingredients and knowing the amounts is very important. And And in case of Down syndrome, this is one of the problems because there are so many genes present in the chromosome 21 and we don't know the function of all these genes. We know only the functions of a handful of genes that have been extensively studied. So researchers are currently trying to understand what are the functions of all these genes and know how much of these genes can we tolerate in our body. So to answer this question, it's very difficult to take a guess and know how much of each of these genes we need in our body. And to do that, we need an animal model that can allow us to do different genetic manipulations because we need to introduce some genes, we need to break some genes and know what they do in the body. To do that, we are introducing this tiny round worm called C. elegans, which is 1 millimeter long, not greater than the size of a sand. And these tiny worms have been extensively used in neurogenetic research because of its many advantages. To highlight a few, especially for Down syndrome research, it is a great model because it has genes which are very similar to several of chromosome 21 genes which are present in humans. And as you can see here, this is something similar to Dr. Pierce showed earlier. The chromosome 21 genes are present scattered across the 6 chromosomes that are present in this tiny worm. And 47 of these genes, they are highly conserved, which what it means is that these 47 genes are mostly identical in worms because of evolution. So this makes it a great model for Down syndrome research. Secondly, these worms can have more than 200 babies, which allows us to test our hypothesis with a bigger sample size, which is a bigger advantage for us. Thirdly, this animal model allows us to do this genetic manipulation very easily so that we can break genes and add excess copies of these genes and see what happens in the body. And also, C. elegans have been, as I mentioned, they have been extensively studied in neurogenetics research and they have been used in many pivotal discoveries and they have been recognized by Nobel Prizes several times. To highlight one, in 2024, the Nobel Prize in Physiology was awarded to 2 worm researchers for their very important contribution. And lastly, these worms have a transparent body and they also have a very simple nervous system which allows us to manipulate these genes and know exactly how they alter different neurons within them. And with these worms as the animal model of choice, one of the previous grad students in our lab, Sarah Nordquist, she went ahead and tried to understand what are the functions of these different chromosome 21 genes. So to do that, what she did was she broke each of these genes one at a time in C. elegans and she tried to understand how they altered worm behavior and development. And she identified that 10 genes had played an essential role in the neuronal functions and 14 of these genes were very important for helping worms develop at a normal pace. And interestingly, Sarah was the first person to identify 2 of these genes which were essential for neurotransmission. And what it means is that it helps neurons communicate with each other and transmit the information forward. So Sarah was the first person to name these 2 genes, which I think is very cool. And no one had studied these genes before she identified them. And another grad student in the lab, she did the opposite. Sophie Sanchez, who Dr. Pierce introduced earlier. What Sophie did was she did the opposite. She added excess copies of these genes one at a time and she tried to see what happens if there is excess copies of these genes. And what she found was almost 2/3 of the genes that she tested, they presented with a behavioral difference which she called as sensitive genes. So these genes, when they were present in excess copies, they either impaired the worm behavior or the development. So what it means is that these genes are like adding too much salt in your banana bread. Would you want to have too much salt in your banana bread? It will ruin your recipe. Similar to that, this is a kind of an ingredient. These genes are kind of an ingredient which which you cannot have excess, otherwise it can have adverse effects with your health. So these genes could be one of the genes to prioritize to understand if they cause any problems in Down syndrome. And some of these genes were also the essential genes that Sarah identified earlier, so which was pretty cool. And moving on, to understand these sensitive genes patterns, we can, as I mentioned before, these sensitive genes can be compared with different ingredients we use in recipes. So these sensitive genes can be similar to salt, because adding too much salt it will ruin your recipe. But there are certain genes which she saw that they didn't present with behavioral difference when she added excess of them. These are the genes that are similar to certain ingredients that even if you add a little bit more, it's not going to ruin your recipe per se. You'll still be happy eating the banana bread. So we were curious to see what is common among these sensitive genes and how do they differentiate between the tolerant genes and the sensitive genes. So to do that, we went ahead and used a very simple statistical analysis, which usually life insurance companies use to see whether for car insurance or life insurance, they see whether how much likely you are to claim their insurance. So similar to that, to explain the statistical analysis, let's look at how we can predict if someone survived the Titanic disaster. So the first thing to do to identify the pattern among people who survived and died, we'll need a list of people, the passengers who were in Titanic, and then we'll need to look at, get some personal information about these people to see what are the characteristics which we believe could have influenced their survival in Titanic disaster, and feed this information into the computer system, do the statistical analysis, and then the data, the input data will look something like this, where each row represents an individual, see whether their outcome was whether they died or they survived, and look at some of their personal information, like whether what was their age, what was their height, whether they were able to swim, which room were they living in that cruise ship, and also which ticket type did they have when they were traveling in that time. And using this information, we can identify which predictor best helped us in differentiating between these people who died and people who survived. And using this statistical analysis, it helps us identify that predictor. And based on this trial data set, I was able to identify that the ticket type, people who traveled with first class ticket, they were more likely to be surviving this disaster. And as we saw in the movie, the lifeboats were prioritized for women and children and people who were traveling in first or second class ticket. So using this analogy, we took a similar approach in seeing how these sensitive genes were similar, and we did the same as we saw before. We took the list of genes that Sophie found were sensitive or tolerant, and we looked at the basic characteristics of these genes which we believe could have influenced their sensitivity. And we fed this information, did the statistical analysis, and we saw an unexpected factor that was common among these sensitive genes. So what was that factor? We saw that the genes, we looked at the distribution of the amounts of these genes in wild populations of sea anemones. So what we did was we looked at healthy worms that were hanging out in different parts of the world, and we saw how much these genes were being expressed, or how much amount of these genes were present in each of these worms. And we made a distribution, we looked at the distribution of these genes. What we saw was, if they were tolerant genes which didn't present with a behavioral difference, these genes on average, these worms expressed some amount. There were few worms that expressed lower amounts of these genes, and there were few worms that expressed higher amount of these genes. And this presented with a really nice bell curve distribution. But in contrast, the genes that presented with a behavioral difference, they seem to have a very clear cutoff, beyond which there were no worms that express these genes beyond this level. So it suggested that there is some clear maximum ceiling, and level, it might be unhealthy for the worm, or it may also affect the survival of these worms. So it suggested that this clear cutoff could be one of the factors to predict if whether the gene is going to cause any medical problems in Down syndrome. And we wanted to see, so this was a pattern we saw in worms, and we wanted to see if chromosome 21 genes in humans can also have the same pattern. And interestingly, our hypothesis was true even for the human genes, because we plotted this distribution and we saw many of these genes had this normal bell curve distribution, but some of these genes, the ones that are highlighted in red, some of these genes have been previously identified to cause major medical problems. Like for instance, when you have extra copies of them. Like for instance, the APP gene, which is known to cause Alzheimer's disease when there is an extra copy present in your body, regardless of whether you have Down syndrome or not. But they are the major risk factor for Alzheimer's disease. So next we wanted to see if we can use this prediction to do the backward analysis, to use this cutoff as a predictor to identify if we can generalize it to other genes present in humans and know whether we can predict these sensitive genes that could be helping in other neurological disorder analysis as well. And to do that, we looked at two major data sets. One was previously predicted to predicted to be present in a region which has more number of tolerant genes. So having extra copies of those genes were not going to cause any major medical problems. And we saw that and then we were trying to look if these genes have that clear cutoff or not. And what we saw was 90% of these genes didn't have that clear cutoff, which was reassuring that our hypothesis could be true. And then in contrast, when we looked at the data set which was previously predicted to have sensitive genes present in that region, we saw that 50% of those genes were having a very clear cutoff. So this reassured our hypothesis that yes, clear cutoff could be one of the factors that we can use to predict other sensitive genes. So this is a really cool discovery that we made so far in Down syndrome, and this clear cutoff pattern could be used as a predictor to see for any other duplication or extra copy sensitive disorders. Can also use this clearly to predict which genes they should prioritize for the research. And I am currently excited to move this project to the next stage and try to see if how much of these genes beyond this cutoff we can tolerate. So for using the analogy of salt, if we keep adding a pinch of salt extra and from the recommended amount and see at what point the recipe starts falling apart. Similar to that, I'm trying to see if I can dial down the amount of genes lower than the cutoff or higher than the cutoff and see if what happens to the worm behavior or development, and eventually in humans as well. And likewise, I'm also trying to see if the tolerant genes, if they work along with other genes and show their if their sensitivity pattern changes, if I try to see their correlation in more than 2D plots in comparison with other genes, if their sensitivity changes, if they are present in excess with some other genes as well. And that plot would look something similar to this, where the hill, it might look like a hill-like distribution with a dip based on how much of a cutoff we see in both the genes that we are comparing. With that, I would like to thank Dr. Pierce and Dr. Sophie Sanchez and Dr. Sarah for all their contributions, and especially Sophie and Dr. Pierce for their mentorship in this project. Thank you and have a good day.
We have time for a quick question before these guys come on. Do you want to ask Swetha or myself questions?
Yes, sir. Yeah. So down the road, what would be some application potentially? when we have mapped this out?
Is your question about mapping out the, using that cutoff as a predictor to identify?
Or just down the road, potentially, there could be some kind of intervention or, development in helping people with Down syndrome.
So my understanding is that if we are able to, so this was a bigger screen mainly to identify what genes to prioritize for testing in higher animal models, because right now it looks a little bit overwhelming because there are 200 genes and time is the bottleneck when we are using higher animal models. So by using this, we were able to narrow it down to a more promising number of candidates, and these are so 28 genes or 13 genes are still doable. So now the next steps would be to test it in rodent models or maybe non-human primates like monkeys or chimpanzees, and then try to see if what kind of behaviors are being affected because of these individual genes, and then we can come up with some interventions.
Gotcha.
I'll just add for context, the typical labs uses mice, and they only have enough mice or money to study 1 or 3 genes at a time. But they're like over 200. And we kind of know that there's so many that people haven't gotten around to studying yet. So there's probably a lot there that are responsible. They just don't have time to go after. So here, very quickly, looking at human data, not mouse data, we can see which ones by themselves are going to cause problems. And now, looking at 2 genes at a time, 3 genes, and also in multi-dimensions, which ones in combination are going to cause problems. You can see quantitatively where, and we can find drugs or treatments to push physiology back into the normal range. And then we can tell our friends who work with mice, hey, why don't you look at these 2 genes? That's an interaction that's going to be profitable. Or talk to drug companies that have targets for some targets there that might be able to push physiology back towards normal. Because if you go to scientists are just like we're human, different genes become popular and everyone gravitates to them. And then you're worried like, maybe there's lots of other things you're missing. So this is a lot more unbiased, systematic analysis. Okay, well, thank you very much. Great.
Okay.
So I'm really delighted to have these guys came all the way up from San Antonio.
Hi, my name is Floyd Jones. I'm a project manager in the clinical trials division for the Glenn Biggs Institute for Alzheimer's and Neurodegenerative Diseases. We are one of, 20 Alzheimer's disease research centers in the U.S. and one of the only in Texas. And I'm joined by Sarah Savoia. She is a physician assistant and assistant professor at UT Health, and she is the principal investigator for the Track DS project here that's being done in San Antonio. And also working with the PowerPoint is Dr. Haritha Karragadda, who is one of our clinical trial specialists and will be presenting on some of the clinical research we have going on at the Biggs Institute. And we just want to thank Dr. Pierce for inviting us. We do really appreciate it. I know we had connected a long time ago, but glad he still remembered us, and we're very happy to be here.
Good evening, everyone. I'm Haritha Karragadda. I'm one of the clinical trial specialists on the team here with Glenn Biggs Institute of Alzheimer's and Neurodegenerative Diseases with UT Health San Antonio. It was founded in 2017 by Dr. Swetha, and in 2021 we were one of the two new NIA National Institute of Aging designated Alzheimer's Disease Research Center for Excellence, and the only one in Texas, and that stands true even today. Firstly, what is Alzheimer's disease? According to National Institute of Health, Alzheimer's disease is an irreversible brain disorder that slowly destroys memory and thinking skills and eventually the ability to carry out simplest of tasks. Why am I here today is to talk about the connection between Down syndrome and Alzheimer's. As many as 9 in 10 people with Down syndrome develop Alzheimer's disease, and Alzheimer's disease is one of the leading causes for death in adults over 25 with Down syndrome. And people with Down syndrome have helped researchers discover genetic relationship between amyloid, which is a main protein in the brain, and Alzheimer's disease almost 40 years ago. I'm sure you already by now, which is repeated 4 times already, or trisomy 21. So the risk is higher mainly because of an extra copy of the gene called APP, which makes the protein called amyloid. So the extra APP results in more amyloid protein. These amyloid protein results in amyloid formation of clumps in the brain called amyloid plaques, and these plaques in the brain are typically seen in Alzheimer's, and these plaques are the ones that release neurotoxins causing damage to the nerve cells. Some of the main symptoms here, memory and thinking are the problems and the main signs of possible dementia. Others include forgetfulness, social withdrawal, disorientation, loss of daily living skills, change in personality, development of seizures, change in sleep patterns, major weight change, aggressive behavior, and loss of speech. And there are tests that can be done for Alzheimer's in people with Down syndrome. Firstly, we have thinking and memory tests which are done by the age of 40, lab tests, a neuro exam, brain imaging like MRI and PET-CT. People with Down syndrome have essentially the same brain changes as those with Alzheimer's disease, but they experience disease at a much earlier age. So if research could uncover ways to slow or to prevent the progression of Alzheimer's disease in people with Down syndrome, it could show us how to target Alzheimer's disease in everyone. Researchers also want to develop deliver the most promising Alzheimer's treatments to people with Down syndrome, but it cannot be done alone. So, Alzheimer's disease is it's the same in people with and without Down syndrome, but there are some differences. It is the way Alzheimer's disease develops and when it develops. Unless there are treatments that are tested in people with Down syndrome, we cannot know what these differences are or how they will affect and how well these treatments will work. At this point of time, the treatment approved for Alzheimer's have not been tested in people with Down syndrome. I think Dr. Pierce already mentioned about this study, the trial-ready cohort with Down syndrome. So what can I do to join TRACK-DS? The trial-ready cohort with Down syndrome currently needs 120 healthy people with Down syndrome, and it is funded by the National Institute of Health's Include initiative with partnership from Alzheimer's Clinical Trial Consortium and ABCTS. By creating a community of people who are interested in learning about research opportunities and are ready and willing to participate, researchers hope to recruit participants for future clinical trials. It is a part of a larger movement in people with Down syndrome to advance Alzheimer's disease therapies and potential cures for general population. Who is eligible? Eligible volunteers are healthy between the ages 25 to 55 with Down syndrome and have interest in participating in clinical research and will be visiting the nearest research center where they're on the study every 16 months for routine exam and brain scans. And each visit typically will include physical exam like blood pressure. It also will include blood draws, a mandatory MRI, and some memory assessments to measure the changes in the brain and brain function. So some of these assessments include learning and naming objects. What is involved is what I went over. To make a difference, you can join the practice study. We do have flyers at the end. Okay, they are placed over there. If any of you are interested, please pick them up, and we are available for questions after. Currently, there are about 12 research centers in the United States and 4 in Europe. And there's also a website if you'd like more information. The whole point of doing this trial-ready cohort is for identifying individuals, seeing if they are eligible for one of the clinical trials. But before I go forward, I want to let you all know that you all can be part of the trial-ready cohort, listen about the clinical trials, say no, and walk away. So one of the clinical trials that we are looking forward to starting and working at the Biggs Institute is the ABATE study. ABATE is testing treatment for Alzheimer's that has not been approved yet. We started by testing treatment in about 40 people with early Alzheimer's who do not have Down syndrome, and the study is now testing the treatment for Alzheimer's in people with Down syndrome. ACTC is helping run the study. About 80 people with Down syndrome will be participating in 3 countries that include Spain, UK, and USA. What do we want to learn from this is to see how the safety profile of the treatment, how it works inside the body, and if it gets rid of the amyloid clumps that I mentioned previously, and if it slows down the memory loss and thinking problems. About the study treatment, the medication is called ACI-24.060. This teaches the body's immune system to get rid of the amyloid clumps, similar to the way the vaccine teaches our body to clear the future infection. In this ABATE trial, individuals who are participating might either receive the active drug ACI or an inactive treatment called the placebo. No one will know, you will not know whether you received the medication. Me being part of the clinical trial team will have no clue, so is the principal investigator of the study. And I also want to add that participating in this, getting the medication or any of the tests are completely at no cost, and reasonable cost for visits. If you're traveling from far, your meals will be reimbursed. Who can participate in ABATE? People with Down syndrome who do not have dementia and between the ages 35 to 50 and have a study partner. One of the main reasons is when we do memory tests, they'll give us amazing answers. What did you do yesterday? Or what did you have for dinner last night? Amazing answers, but then how do I know they are right? So we definitely do need a study partner. And then, as I mentioned earlier, taking part, especially in a clinical trial or any research, is 100% voluntary and it is your choice. And you can change your mind at any point of time. Sign the consent. Okay, I'm scheduled tomorrow, and then the day you plan to come, you're like, I don't want to do this anymore. You're free to change your minds. But of course, I'll call you and be like, hey, why you don't want to come? But and your participation in the study could help us find treatments. So what will happen in the study? The study at the current lasts about 2 years, which will include 19 visits and is divided into 3 parts. First is the screening period, which is up to 6 weeks. This is when the participants and the study partner will be given a consent form. We'll go over that in detail, and then tests will be done to see if they meet the criteria. You will tell us, hey, I'm perfectly healthy, but I need to confirm that. And the treatment period lasts about 1.5 years. this is where 6 injections are given. It could be either the active medication or the inactive placebo. And this would be followed by a follow-up period of 6 months where there'll be regular checks to do to check health status and see how the study treatment has been working in their body. What tests will be done? A general health checkup and a body exam, blood and urine collection, memory and thinking tests, heart function monitoring, MRI and PET-CT, and then we will be asking questions to see if they've been experiencing any side effects and all the other and we'll also record all the other medications that they are taking. Something very important in the clinical trial is confidentiality for the participants. We will ensure that your personal data is kept safe in compliance with the data protection laws. Individuals who do not need to know who the participants are will not be able to see the names or any contact details. Data will have a code number. Only the study doctor and the research team at the clinic will have access to all the personal and health information data. So what happens when the study is over? You can still talk to the research team if any questions come up, even after your participation is done. You will see your own doctors for your regular medical care. When all the participants are finished, we will review the information to figure out what we have learned about the treatments. We will publish what we have learned about the treatment for other scientists, and we will share what we learned with the participants and with people in the community. The next is about the study status and the safety updates. As of now, we've not had any safety concerns with the drug, and for the part 1 of the study, where it was done in Alzheimer's participants, over 40 individuals were enrolled with mild Alzheimer's disease in UK and in Spain. Participants have received either low, mild or high dose of the study treatments. And the part 2 of the study, where we've had individuals with Down syndrome enrolled, more than 5 have been enrolled in UK and Spain. Enrollment in the US starts February last year. And participants have only received low dose study treatment in the United States. And there is a plan for higher dose of study treatment once we know independent committee determines that the drug is safe. That usually happens after the last participant has finished the study period. And finally, if you all want to know more about this information, the study does have a study website, but we do have pamphlets for both the studies right at the entrance. Thank you. We have Savoia, who's the principal investigator at our site. Do you want to come up and say a few things?
You covered the presentation perfectly. So, as Haritha said, if you are interested in learning more about the study, back at that table over there, we have both information about the trial-ready cohort study, and then also about the FATE trial.
And also there is general information on Alzheimer's disease and Down syndrome. If that is something you are concerned about, feel free to read it over and talk with your family doctor or whoever manages your health care. I wanted to ask, are there any questions about clinical research in general or research related to Down syndrome and Alzheimer's disease?
I think you mentioned that people with Down syndrome are not being treated with Alzheimer's drugs
At this point of time, they're not being tested.
Okay.
The safety and efficacy, they're not being tested yet. There are a couple of medications that have been FDA approved for Alzheimer's disease, but they're not being tested in individuals with Down syndrome.
And that's why one of the reasons the trial-ready cohort study was designed, to start getting people with Down syndrome into clinical trials for Alzheimer's disease treatments.
And when you say healthy, what would disqualify somebody from participating? Like diabetes, thyroid issues, like what would be a disqualifier?
Well, typically, I mean, obviously none of us are perfect, But if somebody has medical conditions that are well managed, that is, then they are eligible to participate. The one exception is if somebody is not able to undergo an MRI, like if they have an implanted pacemaker, aneurysm clips, another implanted device where the doctor has said, you cannot get an MRI, if they try to give you one, say no, then we would not be able to enroll them in the trial-ready cohort. For the clinical trial, there is some wiggle room that we can use a lower power MRI, but we usually recommend people talk with us about that earlier because we kind of need to know the details, because some pacemakers are MRI safe at a 1.5 T magnetic field, and then some of the older models are not. And we certainly don't want to wait till they are in the MRI and it's running for us to find out. Any other? Oh, yes, ma'am.
Are they using the Leqembi, or is this a totally different thing that they're just doing all Alzheimer's?
It is totally different. This is basically what they're calling an amyloid vaccine. And we are testing it in individuals who may show signs of having the amyloid clumps accumulating, but are not showing like clinical signs of dementia yet. But no, Leqembi is a recently approved medication. It is, however, not approved in patients with Down syndrome.
And is there any research on the MTHFR mutation that sometimes has been correlated with trisomy 21, but also with Alzheimer's? Is
that will be
in the
a Sarah
wheelhouse?
question.
So for that gene, I've also seen it related for increased risk of stroke.
And vascular.
And vascular. But not specifically to my knowledge, just specifically for Down syndrome.
What about logistics? So if people are living here in Austin, if they want to participate, they have to go to San Antonio for these visits?
For right now, yes. We have had conversations about kind of setting up a satellite site, maybe partnering with Dell, but that's really, really far off. We can tell you that for example, TrackDS, usually it consists of about 1 to 2 visits every 16 months. So this would not be like, every week you're driving down to San Antonio. The ABATE clinical trial is more time intensive because we are giving people non-approved drugs, so we need to make sure that they are being monitored more closely, and so that does require a bit more of a time commitment that we do encourage anyone to consider if they're thinking of discussing it with their family to see if they'd like to move forward with it. Only thing really we could say more with that is we do work with everyone's schedule to find times that work best for everyone, and we do understand that people have routines, they have schedules, they have lives, and we try to mess with that as little as we can.
And traveling, we reimburse for traveling.
Yes, we can.
I don't know if you said it, but what are the results for this drug on non-DS population so far? Is that?
They have not been officially released because basically that phase is just completed and they're still undergoing what they call data cleaning, which is a very, very stressful time for everyone, where we get calls every day saying, we just issued 5 queries in your data, please fix them tomorrow. And so that process is going on, and then once the data is clean and locked, they will do the analysis. Typically in these types of studies where you have a smaller sample size of about 40 participants, it is, usually it is not as involved. We have worked on studies where we have upwards of, 1,500 to 2,000 subjects that we followed over like several years, so that's a much more involved process. But we hope that they will release preliminary results soon, and we do encourage you to keep an eye out for any releases, and then also you can look up the company who has developed the vaccine, AC Immune, and they oftentimes will present press releases once their data has been analyzed and they're ready to present it to the public. Any other questions? Yes, ma'am.
How far are you into this study already, or are you just now trying to recruit?
For the ABATE study or the TRACK DS or E?
The amyloid.
Okay, yeah. For the ABATE, we have been working on recruitment. We have not identified many people locally yet. However, we are doing outreach events like this in case anyone's interested. And in addition, talking about the TRACK DS, if someone might be interested in clinical research later but can't really commit to participating in something a little more time intensive right now.
So are the other research facilities throughout the U.S. actively recruiting for this too, or is it just your location in San Antonio?
They are, yes. So yeah, if you have family or something in Colorado or Madison, Wisconsin, or Massachusetts, and they might be interested, then by all means talk to them. We don't want to fly them down here.
Right.
So.
There are 8 sites in the United States currently are recruiting already. There are 8 other sites in the United States.
Yeah.
The flyer will have QR code to the website, and you will be able to find the locations.
Yes, ma'am.
I just have a question. Either at this UT or at UT in San Antonio, is there any talk about a Down syndrome clinic?
For Down syndrome clinic, I believe Down syndrome and Alzheimer's, I believe Sarah has time devoted in her schedule to see patients where that is a concern. For like Down syndrome in like younger people, we don't know, because that's more handled by pediatrics or family community medicine, and so they're kind of separate from us.
But if there are concerns about memory changes for those with Down syndrome, the Biggs Institute is seeing patients with Down syndrome for memory concerns.